All right, good afternoon, everybody. My name is Richard Moss, and I'm going to be moderating the panel this afternoon. This is the second infrastructure panel of the day, interestingly. The first one, and I see some faces who were at the first one this morning, was infrastructure and investment. And this afternoon we have infrastructure at risk. We have 5 great speakers. The first is Elizabeth English from the University of Waterloo, who's going to be talking about adaptation through amphibiation. I think I said that right.
So amphibiation is a word I made up. Let's see. I think. Yes, that works. And then
Found it. Great.
that works. And there we are. So, yes, I work on amphibious construction, and I got started on that very shortly after Hurricane Katrina. I was doing research on wind effects on buildings at the LSU Hurricane Center, and realized that there was a lot more going on with water than wind after Hurricane Katrina. And essentially, in my search for a better solution than what FEMA was forcing down people's throats, I started working on this, and it's been a very interesting 13 years. So I'm going to start by telling you what is amphibious architecture, because I know there are at least some people in the room who are not familiar with this term. Many of you may be, but so the term amphibious architecture refers to buildings that look like or may look like ordinary buildings, sitting on the ground like an ordinary building, except when there's a flood. And when there's a flood, they float and they stay on top of the water as long as the flood is there, and when the flood goes away, they come back down and sit on the ground again. And so that's why I call them amphibious rather than floating, because floating to me means permanently floating. So floating houses are houseboats, and the work that I do is mostly on houses, and I call them amphibious houses. So what do we need in order to do this? We need to have buoyancy under the house, something to lift it up when the water comes, and we need a vertical guidance system so that it will only go straight up and down. No floating around, only straight up and down. I first learned about the amphibious construction in the Netherlands when I started investigating this, and then shortly thereafter discovered that right under my nose in Louisiana there was a community that at that time had been applying amphibious construction principles for 30 years, not far from me in rural Louisiana. So what I like about it is we do the adapting. We're not trying to control Mother Nature. We're not making walls. We're not making barriers. We're not presuming that we can tell the water what the water should do. We're getting out of the way of the water, and the water can go where it wants. So it's a much more natural approach and works in synchrony with Mother Nature rather than trying to control or obstruct what the water wants to do. So this is the basic principle. Let's see if I've got the pointer here. So this would be, this actually is a model in Vietnam. I'll tell you about that project in a little bit. But this is what it would be in the dry season for an ordinary house, and in the flood season, the water goes into the house. So if you have retrofitted it to become amphibious, then in the dry season, there's buoyancy under the house and vertical guidance posts, and when the water comes, the buoyancy lifts the house, slides up and down on the vertical guidance posts, and after the flood, the water goes away, the house goes back down onto its foundation, and no damage. So this is what they've been doing in the Netherlands, and you can see here it is in the dry situation overlooking the lake, and here's the same house when the water is high. There is also a single amphibious house in the Netherlands on an island on the River Thames, and this is the principle of how it works. So it has a double basement, essentially, and the inner basement is the buoyancy. It's the I call it the concrete bathtub approach, but it floats by keeping the water out, and when the water comes, it floats up. The outer basement fills up with water, and the house floats up as high as necessary. And this is a community building in Poland along the riverfront. And here's the diagram of ordinarily the people walk around up here. That's the embankment. The river is down here. When the water comes, it does this, and that's as high as it can go. And it doesn't need to go any higher, because if it gets that high, then it starts flooding the land. So let's go to Louisiana, and I'm going to show you what they've been doing there for decades now. So it's not beautiful, but it works. So here's a house that was already up on small stilts, and a new owner bought it and decided that the stilts weren't high enough, but he didn't want to put it on higher stilts, so he put big blocks of, I have to call it EPS, not styrofoam, big blocks of, because that's trademarked, so big blocks of expanded polystyrene under the house and some posts that it will slide up and down when the flood comes. The flood this year, it used to be that it flooded most every year, and the houses would be up for a few days or a week. Then it started flooding a couple of times a year, and this year it flooded in January, and the amphibious houses are still floating. They expect to come back down in July or the beginning of August. So here's another example, a little pre-manufactured house showing what it is under dry conditions and when it's floating. This is what happens when you have your house at BFE, base flood elevation. That's the elevation that FEMA requires. It's 11 feet in Old River Landing, and there was a 15-foot flood. So you can see the consequences there. This is what happens if you have an amphibious house. There's the water line on that one, and the one next door, there's the water line. So this one filled up with water, that one went up, came back down, no problem. Most of these are summer places or recreational places. They call them fishing camps. Buddy Blaylock lives in this house permanently year-round. And so here it is in dry. This was just after a flood in 2011, and there's still the mud all over the ground. And here it is floating, and you can see how high up it is by the camp right next door. So it's up to this level. It's floating up to this level in this picture of the 2011 flood. So what do? I don't build a new amphibious construction for the most part. I retrofit. I started this right after Hurricane Katrina, started working on this concept, and the idea is to make it possible for communities, already existing communities, to stay where they want to stay and not be forced to move out. And this is really, for me, it all started with social justice and started with the prevention of trauma and loss, because from the LSU Hurricane Center working in New Orleans after Katrina, I saw a lot of trauma. I think it traumatized me too, to see so much heartbreak and loss and destruction of culture. You know, plants and animals are protected by the laws, but human culture has no protections, and so we need to give it an opportunity to be preserved and flourished, or we will lose it. So I call my group, my research group, the Buoyant Foundation Project. So we work on retrofits. So we have to have the buoyancy blocks, we have to have the vertical guidance system, and since we're working underneath a house, and the house basically, it's like it's sitting on a floating dock, only the floating dock is on the ground most of the time, except when the flood comes. So we have to have some structure underneath to tie it all together. It's not a one-size-fits-all solution. There are particular houses that it's good for. There are particular flooding circumstances that it's good for. Where it's good, it's amazing. Where it's not good, don't try it. It has a lot of advantages. One of them that you're not going up and down all those stairs all the time, so it's good for the elderly and the physically disabled. It doesn't change the look of the neighborhood, and it's expensive. It's about a third of the cost of permanent static elevation, and that's because you don't have to replace the existing gravity load foundation. You don't have to replace it. You can grandfather that in on a retrofit. So the only thing you have to put in the ground is the vertical guidance posts. So we built a prototype at LSU with my students, and that's the process there. And there we were when it was finished. And I have to tell you, when this lifted off, it was a religious experience for me. So this is our conclusion. Really? Okay. Why fight floodwater? We can float on it. So we wanted to do this on shotgun houses. This is the basic principle. I'm speeding up. So that's what it looks like. Here's my little animation of the assembly process. This only uses 20 more seconds of my 5 minutes. So it's a screen around the base so the waterborne debris can't get under the house. So that's the basic idea. And so I have amazing architecture students at the University of Waterloo in Canada, and that lower right picture is a render. That's not a real flood. So don't think that that's a photograph. I'm going to have to go through this pretty quickly, but one of the types, the indigenous communities are really tied to their land and they don't want to leave. In Canada, we call the Native Americans First Nations. That's the name they prefer. So this is a project for First Nations. So we have the Great Lakes here and Hudson Bay. So we're James Bay. So this is James Bay on the Albany River, this little town of Kashechuan. That's the plan, and as you can see, it's on the bend in the river, positioned just so that as the big chunks of ice come down the river like this, they come ramming right into the dike. There's a dike around it. They have more trouble with flooding, with water being trapped inside. Okay, I gotta hurry up. So that's the principle. That's the house, Nicaragua. So I was contacted by a guy who made bamboo houses. He wanted me to amphibiate them. People wouldn't live in bamboo houses. They stucco and paint them to look like masonry. So this is the cultural thing. Community Malakatoya, the government came in, scooped them up, put them in government-built houses far away. They didn't like it there. They left. They came back. They're living in conditions like this. The government won't help them anymore. This is what we want to do for them, the bamboo house, and we put a deck on it for the chickens and chigs. The chickens and pigs, because the people would otherwise take them inside their house rather than leave them behind. Okay, Vietnam, Mekong Delta. So last summer I went to, for the last couple of years I've been going to Vietnam. This is what it looks like in the dry season. This is what the same terrain looks like in the wet season. This is how the houses typically accommodate. Here's my animation for the Vietnamese house. They're typically up on stilts. They're smart, but the floods are getting worse. And so that kind of thing happens. So we're amphibiating them with barrels or jugs and vertical guidance posts and a sleeve around the posts, and the water comes and they float up and down rather than filling up with water. So here's a new house that we're amphibiating in the process. Here, I made that word up too. So with jugs this time, and we've got the posts in, and there it is in October floating. They had a big flood this year. This is a neighboring house. He had to move off the road because they're improving the road, so he moved back down into the rice field. We rebuilt his house there using the same materials, and here it is floating in October. And back here, that's the other house that I showed you before. Then that was in Anjiang province, and now we're in Long Am province. And here's the road. So they put their fronts on the road, and then the back sort of hangs off the road on stilts. And so that was in the summer. And October, after we amphibiated this house, you can see the barrels underneath here. And where the walkway was, they now have what's called a monkey bridge, which is X's like this, and a log sitting there, and then a little piece of wood over here for your handrail to walk along, and it's a good idea to do that barefoot. So here's another house that we amphibiated in that same hamlet from the back. The road's up in front. And after we amphibiated this one, they were so happy they went back and improved the house and put on the new sheet metal instead of the thatch. This is what we found in a neighboring province from the flood in October, and this is what our house was doing. Which would you choose? Okay, so Canada. This is where I live in Cambridge, Ontario, and that's the University of Waterloo campus, and that was my students' design, and this is what we built, and then we put it on the water, and there it is in the ice, and there's going to be a conference on amphibious construction, and I got help from the Global Resilience Partnership and the IDRC and the National Research Council of Canada, and thank you very much. And I have some flyers here if people want them.
That was great. So please join me in welcoming Francis Bui from CDM Smith, who's going to talk about assessing the threats from climate change to Marion, Massachusetts' vulnerable wastewater pumping infrastructure. Let's see if we can get you here.
That is a hard act to follow. Okay. Let's see.
There we go. Perfect.
Great, thank you. So Marion, Massachusetts is a very small community, about 5,000 people. If this is like Cape Cod, Marion is kind of like right in the armpit. But it's really a lovely, lovely town. There's about 5,000 individuals that live there. It was originally settled in 1640. Prior to that, it was settled by the Wampanoag tribe. So CDM Smith has been working with Marion for quite some time. We've worked on their wastewater systems in the past. And as part of the work that's been going on in the Commonwealth of Massachusetts, which is a new, relatively new program called the Municipal Vulnerability Preparedness Workshop. Has anyone heard of that before? MVP? Okay, a couple. So basically, the Commonwealth decided that they wanted to have a consistent methodology and training effort for providers such as myself to serve the communities of Massachusetts. So they provided grant money in order to train individuals, and then they provided grant money in order for those individuals to go and visit with specific communities to talk about their risk and vulnerability. And this happened for the town of Marion. And the town of Marion decided, with different stakeholders who attended these different workshops, that sea level rise and coastal flooding were the top hazards. And the individuals who ended up being at that stakeholder meeting included the wastewater operator, the treatment plant operator, as well as the town planner. And they recognized that their wastewater pumping infrastructure was really at the top of their priority list. Again, it's a very small town, but these individuals were vocal enough to express this. And so as part of that effort, they then applied for another grant through Coastal Zone Management to evaluate their vulnerable collection system and pumping infrastructure. This is Marion. It's really tiny, but you can see here in a little bit of short order that the little orange dots are their pumping stations. And this is what the pumping stations are in terms of the FEMA flood hazards. So you can see that the extent of the flooding does encompass a lot of the town, and actually every single pump station is already in the special flood hazard area. The areas that are in dashed outlines, those areas are called the grinder pump neighborhoods. I am not a pump station designer by any means, and so I also had to learn a little bit more about the intricacies and individualities of this specific community. So these grinder pump areas is where the pump itself is connected to a pressure sewer where the grinding of any of the solids that come out of these communities or out of these homes are done on an individual basis. So imagine 600 tiny little pumps and 600 tiny little grinders in basically in everyone's yard. And all of that does feed to their main pumping infrastructure. So as you can see here, there are several pump stations, smaller pump stations, that feed into a larger pump station network. And that eventually goes to the wastewater treatment plant. And our objective was really to look at it, to do a vulnerability and risk assessment of these 8 critical pump stations and of the neighborhoods in Marion, and to talk to them about improvements and climate adaptation strategies. During this whole process, we recognized that the wastewater pumping infrastructure is really a silo, and that we were kind of setting the groundwork for any other future efforts that would occur through the town of Marion. But because our scope is really limited to wastewater pumping infrastructure, that's what we had to look at. If we had choices, we would have been able to expand and look at all of the different types of critical infrastructure in town. But again, there were there were leaders with very strong opinions and voices about what should be looked at during this effort. So the other thing that the Commonwealth of Massachusetts has done is provided a wealth of data to all of the communities within the Commonwealth themselves, including projected sea level rise conditions as well as precipitation and temperature. And we had multiple conversations with the community about what they wanted to design to, what their plans for the future would be. And we came to the conclusion, notwithstanding of having conversations with their partners and or neighbors, because Marion isn't the only one that's going through this process, a lot of other communities in Massachusetts are as well, was to look at their mechanical equipment replacement, as well as if they were to replace their pumping structures in the future, and what those design conditions and that project life cycle would be. So based on some guidance, we're looking 20 years in the future, assuming that they would replace things starting in 2025, and if the pump station structure itself would be replaced in 2030, 50 years in the future. So we chose the intermediate high scenario. And although it's just a number, we're really talking about time scale. So you can see in the yellow diamonds that that's the value that we chose, and the 2 arrows kind of pointing down is depending on the either extreme case or the intermediate case in terms of sea level rise, where that falls within that timeline. So it's really about buying time, and they recognized that they needed to consider this on a larger scale. So then it came down to, well, if they have this sea level rise number now, what would they actually design to? If we were to replace all of the pumping station infrastructure in all of the town, what would that be? So the New England has a document called the New England Interstate Water Pollution Control Commission document. It's called TR-16. And in TR-16, there's language in there about what designers should be evaluating. So it includes the FEMA 1% chance as well as freeboard. The other document that we had to look at was ASCE 24, which is again a design document, looking at what that future design flood elevation would be. FEMA currently looks at the 1% water level with 1% waves. ASCE 24 talked about the 0.2% water level and waves. So in addition to doing this analysis, we also had to look at what that future wave condition would be with sea level rise. So we ran the FEMA typical overland wave analysis tool and looked at what that future wave condition would be. That's one part of it. Another part was really just to come up with how vulnerable these pump stations were. So at each of the 8 pump stations, we did a site visit, which was pleasant and unpleasant at the same time. We looked at the pump station equipment, what type of equipment. We looked at the structure itself, where it was in relation to the LIMWA, which is the limit of moderate wave action, so whether or not waves could actually destroy this potential building. We looked at wastewater system operations. We looked at whether, if this pump station were to fail, what would be impacted. How many homes, how many critical facilities, how many private properties, where environmental conditions were, what cultural and historical areas would be impacted. And we did this scorecard for each pump station. And this rainbow graphic here just shows what we came up with in terms of a score relative, pump station relative to another. Again, we understood that we were kind of in a silo. We were scoped to only look at this type of infrastructure, recognizing that certainly there are other types of infrastructure that could be impacted. But based on our feedback and our communication with the town, this was where we were going towards. So we looked at all the different impacts, we looked at adaptive capacity, and then we also, that whole sum of everything comes down to vulnerability. That's how we assess vulnerability in this case, given these conditions. The second component to this analysis was we looked at probability of flooding. So again, FEMA provides the 1% base flood elevation, but they also provide the X% chance still water elevations as part of that document that is given. And what we looked at was, well, we don't necessarily want to look at a pump station whether or not it's in or out of the special flood hazard area. We wanted to know more specifically where it was within that range. And so we had ground surface elevation. We had a survey crew that went out there and took different topo points. And then we compared that to the FEMA still water. And we came up with, individual probability of flooding for each of these locations. And then we multiplied risk, vulnerability times probability to get risk. In addition to that, we did a sensitivity analysis and we gave the town a tool that would allow them to provide preferential weights on each of those exposure categories. So what impact to pump station equipment is versus critical facilities, et cetera. And what it really came down to is they could change those, and if you made one 100%, then surely it would impact the total answer. But with their input into the preferential weights of each of these impact categories, it turns out it doesn't really matter, because really it's the probability of flooding that is driving the result for risk. So that was a really interesting exercise, especially for the town, because they were really concerned about how their beaches would be affected, about how their specific critical facilities would be affected. And when they were playing with these numbers, they realized that there really wasn't that much of a change. The grinder pump areas was also a very interesting exercise, not just because the town had a little bit of trouble understanding what risk there was to these specific locations, but how to communicate that risk to these neighborhoods. A lot of the controls for the grinder pumps are located basically like right at your electric meter. And they didn't realize that in the future, they would have to change the location of those controls to maybe roofline, and how that would then affect operations and maintenance and people checking in on those specific controls. So that was, again, another element of what we had to do. So then it gets towards, what do they do? What can they do? So we took all these inputs, conversations with the community, our site visits, history that we knew about the town, and we helped them visualize what would actually happen if something were to happen. So this is an example of the most critical pump station in the town, where the ground surface is at 9 feet and the design flood elevation is 23 feet. So the question, and we brought this up multiple times, is the town ready for this? Can the town be prepared for when this type of flooding could happen? And I'll just say that there was a lot of silence in the town meetings when we were having this conversation. And for us, the easy answer is you need to build a new pump station, right? You would need to build a new pump station at all 8 of your pump stations. But we recognize that that's not necessarily the most economically feasible thing that they can do. There's only 5,000 people in this town. So we brought this up as a point of conversation. And I had just gotten an email a couple minutes ago from the town planner that basically said, you have energized the town in having this conversation now. We didn't understand the extent of what this could be. And so, again, this is just a point that they have to acknowledge and recognize. While we're going through this exercise, again, the easy answer is you need to build a new pump station. The other things that we provided to them is currently there are these holes that their wastewater system operators have cored into the building structure. Well, that's not a good idea. Maybe they should plug those holes. That would prevent some flooding. We provided some insight into the low-hanging fruit that they could do right now, so that in the case that a big storm does happen, they have something, that they're trying to do to avoid that. It's not that bad everywhere, but there are locations where, the increase in what they would do would be effective in order to make sure that these pumping stations are running immediately after a storm. That being said, there are certainly homes in this area that are at grade. This is, again, a pretty historic town with some historic issues that, of course, they need to resolve at some point. And we're just giving them the tools to help them understand what they're facing in the future. So in conclusion, we did this assessment, pretty short fuse, short funding, to look at their wastewater pumping stations. It's really a groundwork for future efforts. And again, I had just heard from the town planner that they're trying to roll this into their capital improvement planning in the future. Next step is to continue discussion on what they want to do. The Commonwealth is supporting the communities and pushing certain initiatives forward. So that's another thing that they're doing. And public outreach, as part of this effort, they really want the residents to know that they're going through this process, using some of the information that we developed to put high watermark information out there, as well as reaching out to the grinder pump neighborhoods. I just want to give a shout out to my co-authors, the town planner, as well as the project manager. And because yesterday I gave a limerick, and then I got some more pressure today to develop a limerick. So here's my shot. You guys can tell me. Infrastructure in Marion is at risk. If we don't try, the residents will go tisk tisk. We push towards future design as projections are refined, or managed retreat will be brisk. Thank you.
Great limerick. So our next presentation is from Roderick Smith of Ducky Johnson Home. Ducky Johnson Home Elevation. How do we flood mitigate and ultimately relocate millions of buildings? And let's find you here.
Good afternoon. I know it's right after lunch, and I'll try and keep you entertained enough to keep you awake. And I'm really happy to be here. Thank you to the Earth Institute and all that have been involved with this really marvelous gathering of people. Of course, I come from the private sector. We elevate buildings and relocate buildings. And so we do that for flood mitigation, and in the future we will be part of this migration. The Great Migration, second Great Migration, I'm calling it. So basically, I live across from New Orleans in a non-levee protected community. It's had 7 hurricane surges in 14 years. My town is now 80% elevated. You can no longer sell the house on the ground, and the ones that are elevated are selling for 30% above list. So that's where we are. We're never going back. We're going to get the rest of them off the ground. My wife swears she's the planning director before she retires in 2 years. So interesting. And 80% of ours were privately funded, so there's a demographic issue there that we're able to accomplish what a lot of populations can't. So here we go. Here's our huge coastal population increase since World War II. Over half of our population lives at or near the coast now. And we have to deal with that because the coast is going to move back as the ocean comes up. I have 4 daughters and 6 grandchildren, and I am going to leave it stronger than I found it. And I'm just about done. I'm in my 60s. Holy smokes. How did that come about? Damages are increasing exponentially. I'm just finishing up work with Ducky Johnson, the nation's largest elevation company. They are in 7 states and 2 territories working on $300 billion of damages. If we even come close to that this year, we will break the bank. I guarantee you. There is not enough staff out there, there's not enough consultants, and there's not enough FEMA out there. We're at a huge tipping point. Okay, U.S. has millions of buildings at the coast that contain hundreds of millions of tons of natural resources. But we need buildings to live in and to work in. We are not bears, we are not cockroaches, we are not marsupials. We have to have buildings and climate control. So how do we get how do we get from this to this? From this to this. We can't do this. We will have disintegration of our government and anarchy if we just try and move everybody back and force them to live in tents like we're forcing people at the border right now. All right? We have to have buildings. Demolition of all the buildings as we migrate back is wasteful. And I've said that a couple of times and you all have heard it. At a time we need to conserve. We no longer have the forests that built these buildings. Construction debris is a huge contributor to our landfills. What we're proposing when we demolish a building is we put it in the solid waste stream. It doesn't biodegrade. It's construction material. It's the 3/4 of our landfills are filled with construction debris, and we're proposing to put millions of buildings in there. We got to figure out where we're going with this. And a lot of these buildings, I'm not saying all of them, some of them are not worth dragging around and rehabilitating, but there's a lot of buildings I've seen torn down that could be relocated safely, new foundations, put back into the marketplace and provide housing. We are 2 million housing units short in this country currently, and that is a growing number. So let's think about the images we're sending to our children, because I'm not going to inherit this problem. Our younger people, my daughters and my grandkids, are going to inherit this and going to have to deal with this. So let's set an example and try and reuse as much as we can. Millions of buildings, moving them is a green solution. It meets the housing needs. It also provides a sense of place. When you leave that coast, you're leaving a place. And if you can take a lot of those buildings with you, psychologically that population will have a reference point, even if it's miles inland. And you will take that history with you as far as the architectural history. People are connected to buildings and architecture. And these are some of the ways that we do it. We move them on wheels on streets. We move them on barges. We are the industry that moved the Cape Hatteras Lighthouse, 5,000-ton structure, half a mile back from the ocean. But we're not talking about the landmarks. We're talking about buildings that we need as a society. Moving buildings and getting them ready to use again creates incredible numbers of trades jobs. Every time we elevate a house, we use all the construction trades. Every time you demolish a house, you have 2 people working. And you're burning lots of carbon to kill that house. And every 1,000 square feet of wood frame house is 250 trees. So I'm just saying, kind of an eco-granddad, sorry. Rather be that way than on the other side, right? Okay, so almost done. I wanted to finish early so we have some good dialogue time, because I'm not sure how we're going to finance this. I know that we have an industry. We have the best industry in the world for structural moving is in this country. We have 500 companies with 1,000 machines, which needs to grow by 3,000% in the next 15, 20 years as we get ready for this process. Sea level rise will require us to relocate at least 30 million people, I estimate. And that's non-scientific. That's just looking at the beginnings of this enormous human undertaking that we're going to do. And I want to propose that we move 10 million buildings. It's not out of the realm of possibility. And that'll help boost the economy. It'll be like a works project kind of concept where lots of people are employed in the relocation of structures and resiting of structures and creating of those communities where those structures will be. Because we're not all going to go high density. You're going to go higher density probably near the cities, but you're down in some of these more rural areas that have to relocate, and you'll have anarchy if you insist that they live high-rise and dense. So we need to think about all these processes and probabilities. So reutilize the buildings, employ millions of workers, prevent millions of cubic yards of debris from going into our limited landfill space, prevent millions of tons from covering our beaches, because we have to do something to, I mean, we're going to have to leave the towers there, and we're going to have to deconstruct the interiors of those towers, and what are we going to do with those towers? Glass, Miami, it's all glass, crazy stuff. And so enable the ecosystems to better adapt to the coming sea, because it's going to be rapid. I claim that the wetlands and the marshlands are going to barely have any time to keep up with the sea as it comes in, because it's just going to be fast, and it's getting faster. So here's my closing shot. This is the challenge of the next several generations of us, and we must succeed. Failure is not an option, and we went to the moon. My God, why can't we move 10 million buildings and 30 million people back? It's going to take awfully hard work, and we're going to have to dedicate ourselves to success, because this is a country that was designed through ingenuity and succeeded through ingenuity, and we can do it together. So thank you very much. That's starting the process right here this week. Policy, location, development rights, legal frameworks, all of that has to come out of the start of this meeting. We have the technology, we have the capabilities, the equipment, and we will grow to meet the demand. But you all have to figure out how we get from there to there, A to B, because we have to figure it out. Actually, our technology is 50 years old. It was created via the interstate system construction that demolished entire sections of our cities, most often the lowest income areas where the highways went through. But back then, we took the buildings and we relocated them, but we elevated them with single jacks. Our machinery, there's only 2 of these lifting machines in the world. We use these hydraulic lifting machines that put all the jacks together, and you push one handle and everything goes up, whether it's a chimney or a wood frame or brick on one side and concrete on the other. It equalizes all the lifting capacity. They're both made in America, and one in Chicago, one in Pennsylvania. So the technology is old, relatively. It's 2-3 generations old, but the capitalization and the training and the crews are what we really need to upscale as we meet the demand of moving all these buildings. Yes, back in the back. Hasn't been studied. We do it all the time. The lifting of the structure, the rigging and lifting of the structure, getting it on the wheels is half the cost of the project. Transporting it is, once you get something moving and rolling. We do envision, instead of boat ramps, because the first structures that will go are on the back side of the barriers, the lowest side, front side is dune side, high side, and all those lagoon systems where all those buildings are at 3 feet above sea level or whatever it is, outrageous in Atlantic City and all these places I've been to in Jersey after Sandy. Those will be the first. So we will put them on a barge, we will bring them across, bring them up into the mainland, and we will have utility-free corridors to where we can just start basically hauling buildings inland, and you'll have to have them pre-designed, pre-sited, and we're just all going to have to work together. It's a huge undertaking.
So I'll ask one question just about how do you factor in the condition of the building, and thinking about things like, is this pre or post disaster? But even pre-disaster, there are a lot of buildings that are not in great repair, and you might be better off taking specific components rather than trying to move the whole thing.
Agreed. we can virtually lift any kind of building unless it's absolutely falling apart. That's our technology capability, brick, stone, concrete block buildings, wood frame buildings. But just as when we elevate a building, we have to have an engineer's certification that that building is capable of being lifted. It's not your standard civil engineering function. There's engineers that have more experience in this than others. So they will, just like when we go to elevate a building under grant programs or even privately financed, we have to supply the city with an engineer's statement that that structure is stable enough to be relocated. But we have 150 years of experience in this country with our structural companies, so we know which buildings are really not worth it and which ones are, but we'll have to figure that out because remember, as my wife, who's the director of planning in our community, tells me, those 1,200 square foot houses are the house of the future because of our single family composition and our smaller families now. So all of those little houses are really almost even more valuable than those 4,000 square foot houses. But those big giant beach houses can actually be cut up into 4 or 5 apartments because we're going to need a lot of housing quickly. And so we don't have the force anymore to build the wood frames. And are we going to build concrete block houses for all these relocated people? Because that creates a heck of a lot of CO2, concrete. So anyhow, just another thought process for the week. So thanks.
Thank you. Great. So now we're going to hear from Sara Newkirk of the Nature Conservancy, who's going to talk about the Coastal Act, power plants, and the case for underdevelopment.
It's actually the case for undevelopment, and I made that word up too, or somebody in my my company made it up. That's all right. This is actually, this is a law talk. I'm in this section with engineers, and I need to do the presenter view. This is it. All right. Yeah, so and the title of the talk is The Coastal Act, Power Plants, and the Case for Undevelopment. And I am giving this talk on behalf of myself and my co-authors, Molly Milius from Stanford University and Sarah Ryder from the Vermont Law School. And this is based on a paper that was published 2 years ago in the Vermont Law Journal. So, has anyone seen this face? You tried to feed a child something that he doesn't want to eat. I see it almost every day. They don't want to eat anything. When I was 8, though, my mother came home with a delicious takeout dinner. And it was something that you might describe as nuggets. It was deep fried. It came with a delicious mayonnaise-based sauce. And it appealed to my 8-year-old sense of needing to eat as much fat in any sitting as humanly possible. And so after eating about a dozen or so of these nuggets, I thought to ask her what they were, at which point she promptly told me that it was calamari. And after the shiver of horror that went through my body as I realized I'd just sat and eaten nearly an entire squid, I said, gosh, it turns out that I like calamari. So this is an age-old parenting strategy that my children refer to as cheating, but I refer to as opportunism, and it almost likely led to the development of chocolate milk and other things that we all love. But the reason that I bring this story up is that the premise of this talk is that undevelopment is a controversial concept, and managed retreat is what I mean by undevelopment, and as a controversial concept, it may go down easier, as many bitter pills do, accompanied by other things that are socially desirable. So in the case of my stories, that is tartar sauce and a fry-later. In the case of the case study that I'm going to discuss with you, it's a legal mandate, a different kind of legal mandate than we're usually talking about. So let me introduce you to the town of Oxnard, California. Oxnard is a seaside community of about 200,000 people to the north and west of Los Angeles. Parts of the community rank among the most disadvantaged in the state of California. And also, according to Cal EnviroScreen, they are among the most pollution burdened as well. In consequence, the citizens of Oxnard have been struggling against a history of coastal industrial development that is, quite frankly, very hard to get rid of. But Oxnard also has an incredible asset. This is Ormond Beach. Ormond Beach represents one of Southern California's most intact and contiguous ecosystems of dunes, beaches, and wetlands. The area is home to more than 200 species of migratory birds and provides a buffer against the impacts of sea level rise and climate change, making it a unique restoration opportunity for Southern California. The fact that it is conserved and backed by agricultural land use means that as sea levels rise, we will likely to have room, these ecosystems will likely have room to migrate into, especially if those farms and agricultural areas can be kept in agriculture through conservation easements or other strategies. But look a little bit closer. Is that a power plant in the middle of all the conserved land of Ormond Beach? Yes, yes it is. This is the Ormond Beach Generating Station. It is a 430 megawatt natural gas-fired power plant right smack in the middle of the protected Ormond Beach complex. The Ormond Beach power plant is a peaker plant, which means that it is not online all the time. It only runs during peak operating, peak demand. The Ormond Beach power plant is also what's called a once-through cooling power plant, and meaning it cools its generators with seawater. Once-through cooling was state-of-the-art back in 1959 when the Ormond Beach Generating Station went online, but it is not anymore. And in case you're not familiar with this concept, the idea is that seawater is pulled directly in through open pipes. And the idea is to pull it directly from the ocean along with the fish and other critters that live in it, run it through a screen, which some lucky fish can't fit through. If they win the lottery, they get rerouted back to the ocean. Unfortunately, many of them do not, and they are killed when they're impinged and thrown in the garbage. If they make it through the screen, they are lucky enough to witness the process of once-through cooling directly. Usually they die in the process, and so it's not really that good for them either, but they are returned then with the wastewater as the warm water exits the plant back into the ocean, open ocean. If this sounds archaic, it is. It is also illegal, at least on the books. It's been illegal for a long time. So this is the section that gets sort of into the details of the law. So for a long time, Section 316B of the Clean Water Act requires that all power plants, both new and old, install the best technology available to cool their generators. This is to minimize the environmental impacts of cooling water intake structures. And in 1977, the EPA, for the first time, wrote 316B regulations. Unfortunately, they were remanded by the Fourth Circuit due to procedural defects. Apparently feeling deflated, the EPA failed to propose any new regulations for 15 years, but in 1993, frustrated with this, the environmental groups sued the EPA successfully, such that within another couple of years, they actually proposed new 316B rules. Unfortunately, they only did it halfway, and their new 316B rules only applied to new facilities, not existing facilities, and it was another several years before they proposed regulations that would apply to new facilities. Once again, they did a lousy job, and so all this other litigation happened until in 2014. Remember, in 1977 was the first 316B regulations. By 2014, we actually have workable regulations. But California and New York got sort of sick of all the BS in between here. In 2010, they wrote their own regulations requiring best available technology for new and existing power plants. And strangely enough, this is closed cycle cooling or dry cooling. It's not open water intakes and once-through cooling. So when it was enacted in 2010, the once-through cooling phase-out regulation in California affected 19 once-through cooled power plants. the use of once-through cooling has now been phased out from 10 power plants representing more than 10,000 megawatts of power. The retirement of the once-through cooling power plants with another 6,300 megawatts of power is expected by 2020 and the rest by 2029. So to be clear, there was the opportunity to shut down 19 power plants with aging infrastructure and antiquated cooling systems. And for 10 of them already, we didn't. We missed the opportunity to reclaim coastal real estate and to make the beaches nicer and remove this antiquated cooling water technology. And I tell this to you in the context of this large conference because some of you only got your 316B regulations a few years ago. We've had ours since 2010 in California, so this is a process that you're likely going to be embracing yourself, is what to do. Should we shut the plants down or should we do something else? And in California, our rules require either that you shut the plants down or that you repower them using best available technology. And again, so this is an opportunity to do managed retreat on something that is somewhat less controversial than taking people out of their homes and moving them. So the question as to why there were so many power plants on the coast in the first place relates to the once-through cooling technology. The reason it's so hard to get them off, and the reason we're declining the opportunity to get them off rather than to repower them, goes back to ancient history. So a few years before the OPEC oil embargo in the early 1970s, California's electric utility companies warned the legislators that there was a separate impending energy crisis. And the problem, according to the utilities, was that regional and local governments in California were making it so difficult to site the necessary new power plants that they were unable to do this. They warned of blackouts and brownouts of indeterminate length. And so in order to get in order to get new power plants sited, they needed to have some additional regulation. So this resulted in the Warren-Alquist Act, and that created the California Energy Commission, which remains California's primary energy policy and planning agency. It sets forth the state's policies concerning the generation, transmission, and consumption of electrical energy, and also establishes a comprehensive siting program for review, evaluation, and certification of power plants proposed to meet forecasted power demands. In any event, it's also important to mention that the Warren-Alquist Act has done some fabulous things in California. It has set energy conservation and efficiency standards, which has made California actually a longtime leader in energy efficiency. In any case, this all happened several years before the Coastal Act even was born. And so when it was enacted, we were still in the middle of the energy crisis, and the CEC retained almost complete control over the power plant siting. Which is not to say that the Coastal Commission has nothing to say. It and everybody else in California does have something to say about this process. The water boards, the SACWIS, the Public Utilities Commission, all of these agencies are empowered to do something in the process of power plant siting. But the Coastal Commission is only empowered to provide input on the process. No permit is actually required from the Coastal Commission. And so the CEC is free to ignore the Coastal Commission's input if it wishes to. And so sometimes the Commission just doesn't even bother. But we have other ways. And the Nature Conservancy doesn't usually advocate for or against any particular project. But we did think that it was important that the CEC and the CPUC know that the plant was vulnerable to sea level rise. In fact, as our comment letter said, it's not only vulnerable to sea level rise, it is vulnerable to flooding even without any sea level rise. And that was just what the community needed. For the reasons I mentioned previously, this was a community that was primed to, let's say, be pissed off about how their shoreline had been treated over the centuries. And they were working very hard to ensure that this power plant was removed. To be clear, Oxnard has not just one power plant, but two, and a Superfund site. And to the extent that they needed any reason to deny the permit beyond the environmental justice issues that are pretty obvious with sea level rise, they had it. So the city made their views known, and the Oxnard City Council passed not one but two moratoria on coastal power plants. The Mayor Pro Tem, Carmen Ramirez, told the press, why in the world would anyone want to have a critical electrical facility in the middle of the coastal flooding zone? But there's some additional context. In the background, of course, is the reality is that in California, electricity usage peaked in 2008 and has been declining trend ever since. Meanwhile, the energy supply that's been fueled by all the investment made during the energy crisis has continued to rise. Also in the background, California has been seriously investing in renewables. So much so that the commitment that Governor Jerry Brown made to 100% renewables recently is cool, but not breathtakingly so. We know how to do this. California is actually a net exporter of renewable energy. So the end of the story is that the CPUC and the CEC both denied the power plant its permits, not just for the Ormond power plant, but for the Mandalay plant and one other in Southern California. Shortly thereafter, GenOn, the subsidiary NRG that owned and operated these plants, went bankrupt. The plants have been or are being decommissioned, leaving one to wonder what could have happened if the 10 power plants that were repowered with closed cycle or dry cooling had followed a different narrative. How much retreat could we have had then? There's a postscript to this happy ending, and that's who in this room has experienced demolishing or recycling a power plant? Yeah, me neither. But because the Nature Conservancy and the City of Oxnard and the State Coastal Conservancy own so much of the surrounding land and have been protecting it in Ormond Beach, people are looking to us for answers. So the good news is that they apparently have answers and that there's a whole conference on power plant retiring in Lexington, Kentucky, or at least there was a couple of months ago. The better postscript here is that while development has the look and feel of permanence, the truth is that we've been doing managed retreat in the coastal zone for a long time. Most of us don't remember that Southern California was heavily developed to accommodate oil production, and that what you're looking at on the slide on the top is the Huntington Beach in the 1920s, and on the bottom is Huntington Beach today. Sometimes the development decisions that were the right thing for a particular time and place turn out to be the wrong thing as time marches on. And so as other speakers at this conference have highlighted, we need to continually re-envision our shoreline and set goals for retreat that reflect our current values. Thank you.
We have a clarifying question for Sara.
That's the Calco Superfund site next to it. Was that an oil production?
It's a metal smelter.
Oh, wow.
Yeah.
That was
Good stuff.
constructed with the legacies.
It's capped now, and
The ocean comes in.
exactly. And we studied the question of whether there was a way of expediting Superfund remediation in the face of sea level rise. But it turns out that so many of our Superfund sites, not only in California but around the country, are in the flood zone that it wouldn't be meaningful to expedite those. They would all have to be on the fast track. So, thanks.
Right, I don't know if there's a
Did you get it?
see PDF viewer
Yeah, I think
there.
you can just view. There we go.
Great. So our final speaker before we go into a discussion is Dylan McNamara from UNC Wilmington, where once upon a time my son hit a home run in a D1 baseball game.
Nice,
Yeah.
nice.
And he's going to talk about the dynamics of abandonment along human-occupied coastlines.
So,
Welcome.
thank you. Try not to get whiplash here. We're going from engineering to law, now to physics. Everybody's favorite. On the good news is that I don't have to motivate my talk the way that I typically do when I go to conferences. Usually I put the words abandonment or collapse in my talks, and it takes a while to orient the audience to that idea. I don't have to do that here. The one thing I will do is to kind of personalize the story. I live about 2 miles inland from that picture that you're looking at there. So what I decided to do last summer to help motivate talks when I have to is I took a GPS unit down to the beach and measured the elevation of parking spots when I commonly go to the beach, what their elevation was to sea level, and that's what I found. And I was actually kind of surprised that they were as low as they were. So given sea level rise and so on and so forth, it's a problem. communities like that, that image there, significant economic development on top of a coastline, in this case, Barrier Island. Big transitions are coming for those locations. That's not news to this audience. I will point out the National Science Foundation. They've been very helpful supplying resources to me throughout my career to investigate some of these dynamics. So what I'm going to have to do in this talk, rather than spend time motivating it, is kind of put this idea, the overall question for the conference, into the context of the way that I think about these systems. So at what point managed retreat? So first I take the word managed out because I feel like in these systems, the idea that they're going to be managed by some sort of collective higher level place in a clean way is kind of unrealistic given the economic and political context that they're in. I think it's going to be a fairly haphazard retreat. And then the word retreat, there's been some wonderful discussions about that word and the connotations associated with that word, and I think those are really important conversations to have. As a physicist, I'm going to sort of make this an objective question, because to me, when I think about this transition, it really is, at what point instability? And leave it to a physicist to take this really complicated question, and now we're looking at a ball and a bowl. But if you'll bear with me, I want to introduce you to some of the jargon that we use in my field to think about instability, and then show you how we can apply that to this very complicated issue that we've been talking about for the last couple days. So the ball likes to sit at the bottom of the bowl. That location is sort of a steady state for the ball. We refer to it as an attractor. It's an attractor in its phase space. And so the phase space is the thing that I'm showing there on the right-hand side. The phase space is a space whose axes are the things that you need to completely describe the system. So in this really simple system, all you need are position and velocity of the ball. And so the attractor, the bottom of the bowl that the ball likes to sit at, is position 0, velocity 0. And so attractor is indicating the idea that if you were to do a simple experiment, you kick the ball up, it will come back down and rest in the attractor spot. And if you think about that in terms of the phase space, you kick the ball, give it some different velocity, some different position, it will follow a trajectory in that space and land back at the attractor position. So the attractor sort of sucks it in from other positions in that space. So now if we take the walls and make them a little shallower and do the same experiment, the same thing happens. In the phase space, you kick it out, give it some new velocity, some new position, and it will wander and find its way back to the attractor. The difference is that now the route that it took in getting back to the attractor position was it took a little bit longer. So if we keep playing this game and make it unstable, it's pretty obvious if you tilt the walls just such. Now any little kick, and in that space there, it'll just fly off to infinity. So I'm not so much interested in this, because I don't think this has happened quite yet at the coastline in any large sense. I'm more interested in the transition. When the walls went from being steep to shallow, the important thing I want you to take away is that in the phase space, the flow went from being strongly convergent, so it sucked it to the attractor very strongly, to being less convergent. It kind of wandered its way through the phase space and eventually found itself at the attractor. And that's an important distinction as the system was heading towards instability. Okay, so keep that with you. And so my question is, can we take that same approach? Can we find the phase space for this complicated system, like Wrightsville Beach or coastal communities writ large? Can we find the phase space that they're in and then explore how convergent that flow is in the space? And then can we say something about the evolving stability of the system based on how strongly things are converging in the space? Okay, so the really difficult question that I won't have time to answer in any satisfactory way is, how do you come up with the phase space for this very complex system? I will just kind of do a quick flyover of how you do that. It's a technique called attractor reconstruction, so I'll explain that in a second. And then once we've done that, once we've rebuilt this phase space and we've seen how the flow looks in that phase space, how strongly it converges will be a measure of how stable the system is. And then this is all heading towards one single plot at the end that we can take some really key policy implications away from. So the attractor reconstruction, I'm going to slightly complicate the system a little bit more. This is the famous Lorenz system. Some of you may have seen. So the Lorentz system, just to say it quickly, is just it's a system with 3 degrees of freedom, x, y, and z. They're coupled ordinary differential equations that if you solve that system of equations, you get time series that look like those that you see there for x, y, and z. X, y, and z are things like measurable quantities, temperature differences in atmospheric convection, and a very simplified representation of atmospheric convection, blah, blah, blah. Doesn't really matter. What does matter is that when you look at that time series, it seems really irregular, but if you plot that system in its phase space, where the axes are x, y, and z, and so at every time you put a point in there, and at the next time you put another point, and so on and so forth, and you trace out that trajectory, now it has this wonderful shape that's very famous called the Lorentz butterfly, captures all of the behavior of that system. And it's a chaotic system. It has sensitivity to initial conditions and so on and so on. That's not important. But the important thing is that is the system's true attractor. So attractor reconstruction is the following thing. If you had just measured x, can you recapture that entire attractor? That's the question that attractor reconstruction attempts to answer. And you can with what's called Tocken's theorem. So we went from law acts to theorems. So Tocken's theorem says if you measure just a single dynamical variable, you can embed it in a multidimensional space and recapture basically the entire attractor. So it's kind of an amazing tool. If you had just measured x, you never saw y, and you never saw z. If you embed that in a space whose axes are x on one axis, a lagged representation of x on another axis, and then a doubly lagged representation of x on the other axis. If you do that, you will, and how you lag it and how you choose how many dimensions, there's a whole industry associated with that. We can talk about that if you want. But bottom line is, it effectively works. If you do it, as you can see here, you reconstruct the attractor. And so geometrically, you've got the same shape that you had before. Topologically, it's the same thing. So now that we have the attractor, we can play this game that we were talking about at the very beginning, where we can see how strongly the flow converges in that space. Even though we only measured one variable, we have reconstructed the whole system's behavior, and now we're interested in seeing how strongly the flow converges in that space. So what I can do with a computer is I can put a little shape in there, like a sphere that surrounds the attractor, and then watch that sphere get smaller and smaller and smaller as it converges into the attractor. And how fast it's getting small is telling you something about how stable the system is. The faster it gets smaller, the more stable the system is. So I've done that for the Lorentz system here. So the vertical axis there is the volume of that sphere divided by its original volume. Time on the horizontal axis, and if you look at just the black line, starts out high, and then as time evolves, the sphere closes in and goes into the attractor, and it gets smaller and smaller and smaller, so the size of the volume is going down, down, down. The nice thing about the Lorentz system is there's knobs on there. I can change parameters and purposely make the system less stable, and then do this whole game again. Attractor reconstruction, put the sphere around it. Now see how fast the sphere shrinks in. So when you do that, you get the dotted line. So it is less stable. So to make the connection with the ball and the bowl, steep walls is when the volume contracts really rapidly. The shallow walls are when the volume contracts a little bit slower. Now for the fun stuff. Property value. So I have access to, thanks to my colleagues, property value for all these locations up and down the East Coast and Gulf Coast of the United States. And what we have done is to take that, and so here's an example of that in the county that I live in. We have taken the raw property value my colleague has and regressed out structural attributes like number of bedrooms, square footage. You take that stuff out, and you get a price index for that county. So there it is. That's one of them. And then some other stuff that we had to do that I don't have time to go into the details of. We have to detrend a little bit, right? Everybody knows there was a big real estate boom in 2008. We have to kind of get that out of there because we're really only interested in the kind of wiggles that are happening on a higher frequency than that. So we detrend this data set. And then once I have that time series, it's just like X and Lorentz in some sense. I can embed it appropriately, follow all the rules that I'm supposed to follow, embed this property index in a space, and it turns out, don't get your hopes up, I'm not showing you the attractor because it's higher than three-dimensional, so it's not, there's no way to look at it. But you can put it into a space and feel confident that anything that's strongly coupled to that property value is represented in that space. And so at some level, you've captured the dynamics of the whole system. on the time scale that you're interested in. And notice my time scale as we go back from 1989 up until 2016. So I've done that. I've reconstructed the giant coupled human coastline attractor. And then I've done this game of putting a shape around the attractor and seeing how fast that shape contracts. So this is what we get. And same axis that I was showing before, volume in this higher dimensional space through time. And so what I've done is I've reconstructed the attractor for two cases, the early part of my time series and the latter part of my time series. And I've only done it for the locations that do not engage in the act of beach nourishment. Beach nourishment, for those who don't know, you go grab sand from some other place, you put it on the beach to fight erosion, increase the height of the dunes to suppress the impact of small and medium-sized storms. So I'm only looking at that data for right now, only places that do not nourish. And what we see is there's the indication that as time has gone on, the system seems to have become a little bit less stable. Okay? If we do the exact same exercise, but just for the places that nourish, the opposite thing happens in a pretty dramatic way. So for places that nourish, they were less stable than they have become more recently. That's a very provocative suggestion. These places that are actively engaging in mitigation are stabilizing. They're getting even more strong to exogenous shocks, or recovering even quicker. So, pun intended, are these places too attractive? You know, my town, Wrightsville Beach, that engages in beach nourishment, is it too attractive? Having just lived through Florence and seen how quickly things get put back together, it's kind of amazing. Anecdotally, it seems like it is happening much faster than it used to. So just to conclude and then come back to the question, I'll answer the question for the whole conference right now. So just to conclude, this attractor reconstruction technique, we measured the flow convergence. Coupled human coastal systems seem to be becoming less stable in locations that do not nourish and more stable in locations that nourish. So what this is hinting at is something that a lot of people have talked about qualitatively. And even I have some papers that talk about this at some level too. This idea that mitigation with a short timescale perspective can build in feedbacks into the system. You beach nourish, increases property value, incentivizes even more beach nourishment, increases property value even more, allows for subsidized insurance now. Now you borrow money from other places to do this nourishment because you have all this high property value, and so on and so on and so on. All those feedbacks, what they seem to be doing is tightening the system up so that when shocks happen, it gets put back together even more rapidly. And I think that one of the important things to think about is, yeah, there are important policies to think about on a long time scale, but some of the short time scale policies that we have right now are really preventing a lot of these locations from adapting the way that they should and even engaging in this conversation about long time scale policies. It's actually worse than that. They're setting them up for a precipitous collapse even more so by having all these feedbacks in there. And with that, I'll end.
So we have time for quick questions, and why don't all the panelists come down while we get ready for the discussion. So if that, any question, clarification? So I'll start by just observing that it really isn't just engineering and physics, right, and law. We also have architecture.
Oh, sure.
With Elizabeth, which is quite different than engineering. You know, I guess, you know, maybe I'll start with you know, one thought. Which is to ask those of you who were, you know, so we have both kind of private sector and cities and, you know, public entities represented. As you guys think about this, how do you see the role of the private sector and the cities, say, interacting in trying to figure out what this process looks like? Because I think some of you were talking about things that helped buy time. Others of you were talking about things that make the sort of deconstruction or retreat process less environmentally damaging and perhaps more cost-effective. And so I just wonder from that if you see, different relationships between the way that cities and states are working in these different contexts.
My comment to that is we, as those in private sector, are there to help communities, especially in small towns and communities when they don't have the latitude or space. They don't have the expertise. They don't have enough time in their own days. They do rely on us to help them make the decision, to help them be informed so that they can inform their residents. And I think it's really from that role where we are advisors, right? That's what we are here for. That's what we're being paid for. That's what the states are supporting us to do, is to step in and to help them make the decision.
I would add, in the story that I told, part of the problem I think that was experienced is that the sort of legal mandates that existed had inertia, and that they were sort of inert to the changes that the coast was experiencing with climate change, and that the real driver of the outcome in that story was the private sector. In the form of the local environmental justice groups that really sort of demanded a different outcome, where sort of the public legal structure was slow to change and react.
I have a bit of a different relationship with the public sector in that I don't deal directly with cities or states very much, but I deal with a lot of restrictive federal regulation, and then also looking for federal funding to support my research. So it's sort of one hand gives and the other takes away is my relationship with the public sector.
And I know Elizabeth from way back in post-Katrina when we first met up, when I got to New Orleans. I followed her work, and it is phenomenal, and she's making headway, just ever so slow. Whenever you're pioneering something, it's ever so slow. I deal with both property owners. I've elevated 1,500 homes in 10 years, and before that, 30 years of rebuilding flood and fire damaged structures. So I've probably held 300 to 500 people in my arms crying. I deal with trauma. I don't know why I was put in the position to do it, but I bring people's homes back to them. Only now we have to bring them back stronger and resilient, and or relocate them in the future. So I do also specialize in outreach education. I've pioneered a whole series of programs post-disaster to go into communities in the gymnasium type setting or the community building setting with the survivors to explain how the elevation process works, because we may have elevated 36,000 in Louisiana since Katrina, but New York has elevated a few thousand, and you have 400,000 of these old buildings sitting in your flood zone. So I also interact with cities a little bit as an industry when I'm in these public forums. So I guess I kind of run a whole gamut of experience in there. But I do try, and my presentations are very reality-based. I go in with empathy, and I educate, and I empower people to make decisions for their property outside of all of the politics that's going around us with all the climate change and everything else. I try and help them get the tools to make decisions, usually in a very difficult, traumatic post-disaster situation.
Yes.
Elizabeth, you mentioned difficult FEMA regulations or difficult federal regulations. What was your experience then, or have you had experience with new construction or substantial improvement structures and meeting FEMA and National Flood Insurance Program construction standards? Okay, when I started meeting up with FEMA, amphibious construction in the United States was essentially totally prohibited officially by FEMA's interpretations of the statutes setting up NFIP. I made friends with the people at FEMA that went to the conferences that I was going to. In fact, I kind of stalked them. And it only took me 7 years, but they changed their policy. So, and I figure if I can move FEMA in 7 years, that's pretty darn good. So now FEMA allows retrofits for properties where it's not substantial improvement. But if you have an NFIP policy, they will take it away. So that's the thumb on my head, and I think that's not appropriate. I think if you have an NFIP, National Flood Insurance Program, administered by FEMA, if you have an NFIP policy and you make an improvement, that shouldn't be cause for removing the policy. But that's my next persuasion for FEMA. But at this point, they use the NFIP to discourage amphibious construction. When I started out, they told me that if I persuaded any municipality to give me a building permit, that would seriously jeopardize that municipality's good standing with the NFIP.
There's your government for you.
Yeah. So.
Yes.
As soon as I get another grant. The Canadian, I did have a Global Resilience Partnership grant for the Vietnam project, but that has been completed and wrapped up. I'm looking for a scaling up grant, but I haven't found one yet. The National Research Council of Canada is supporting the work that I'm doing now, but it's just 2 prototypes. And also beginning to develop guidelines that could lead to building permit. And it's the goal of the NRC for Canada to become the first country globally to have amphibious construction included in the National Building Code.
Okay, brief, because there's a couple of others. No, go ahead.
I mean, sure, and that I think the sort of the point of my talk is that there's a lot of, it's not, we've been talking at this conference a lot about houses and neighborhoods and so forth, and that is actually maybe the hardest conversation to have. Nobody loves power plant. I mean, you don't look at a power plant and go, oh my God, this is this makes our neighborhood so quaint and beautiful. A power plant, it's a necessary feature. We need to have them. We need to have power. But they no longer have to be on the coast. They no longer have to, this was a natural gas-fired power plant. I don't know the direction of sort of nuclear power, but there's, there's a massive move right now, certainly in California, but it looks like around the country toward renewables. The problem that I'm describing here is inevitable. It's going to repeat in a lot of places.
Great. So we're running towards the end of time, so I'm going to take a few questions at once. We'll go in the back row.
So we've heard a few times during this conference, and most recently in your talk, Dylan, about beach nourishment, and I appreciate that those communities become more stable. I'm wondering if anybody knows what happens to the communities that where the sand and other nourishment materials are.
It's a great question. I guess the short answer is most commonly that sand's taken from well offshore. But there are important impacts that happen spatially, interestingly, not exactly as you asked it, but once the sand gets put on that beach, it changes things for neighboring beaches, sometimes in positive ways, sometimes not so much in positive ways. It's a complicated thing. The one thing I can say is that I don't want to make some claim about beach nourishment's good or bad. I just think that people have to think it through very clearly with regard to the dynamics and these feedbacks. Not only that, but these spatial impacts are very important as well. The idea, you get into some of the nasty feedbacks can come about when you're kind of myopically saying, for my town, this is what I'm going to do. Forget my neighbors over here and over here. I'm just going to kind of do the thing that's good for me. And you can get into these kind of battles where people are getting preferential access to these sediment resources. Other towns are getting left out. So there's a whole lot of really, really important questions that people need to keep in mind when they're thinking about nourishment. So it kind of needs to be managed at a larger spatial scale and thought about in a longer time scale.
The executive director of the American Shore and Beach Preservation Association, Derek Brockbank, is at this conference. So please come find me and I will introduce you.
Great. So in the back.
Yeah, quite a mix. I've learned throughout my career, and I'm still learning the best way to do that. And part of that learning has come from NSF. Most of my research has been funded by NSF. We've always had to have broader impacts. At the beginning of my career, those were just workshops at the end of my grant where we'd invite a bunch of practitioners in and just show them these kind of gobbledygook technical results, and it didn't go over very well. Cut to today, and we're actively involved with some of my colleagues, one of whom's here, in trying to establish a research coordination network and bringing practitioners in right from the very beginning and talking to them and understanding the dynamics through their eyes and the things that concern them. We've had really interesting conversations with town officials in different places up and down the East Coast. So we are now, I guess the change is that we're trying to actively engage them at the very beginning rather than waiting to the end and throwing them a distilled version of our conference talks.
Great.
And again, I'll advocate, which I'm happy to introduce you to Derek, and I can make sure to reach out to him, and maybe we can huddle up at the end of this.
Yeah, and I will say I'm good buddies with the Army Corps guy in Wilmington. So we get together a lot and talk about this stuff, and his ears are open to these ideas, and for sure.
Okay, I'm sorry, we'll have one last question here, and then we'll have to stop.
Where you go through a system whereby beach nourishment just is not going to cut it anymore, and it's all gone.
McNamara and Keeler, Nature Climate Change 2013, I think it is. So yes, we have, and we do have a publication. I can give you a better reference than that, but there's a lot of interesting things. It's similar to a stock market. You see a lot of volatility right before the end. People are kind of trading things around much more rapidly than they typically do. What we did in that was actually played around with people's expectations. The way that abandonment occurred depended very, very strongly on how people form their expectations of what's happening, whether they sort of look to the past and project into the future based on the past, or whether they have these more nonlinear ways to project into the future. Not a huge surprise, but we just quantified the role that plays. Yeah.
Great. Well, so if you have a question we didn't get to, please come on down, but let's join me in thanking again the speakers for a great panel.